Hello again, physics friends. We are going to use a previous example that we were working on for time dilation practice and extend it a little bit to show that that example implies that the object's length must depend on its speed. And in particular, the problem was that we had two clocks attached to a racetrack on the ground and Alice flying by in her rocket. So you might remember what this looked like. It was the following. We have in the track frame Alice in her rocket and zipping by a racetrack, and there's a starting line clock and a finishing line clock, and Alice had synchronized her clock to match the starting line clock when she was at the starting line, so they both read 0. And because in the track frame the starting and ending line clock or finish line clocks are both at rest, they're going to have the same reading, and that's true in all pictures. We then were told that the finish line clock read 100 when Alice reached the finish line, but because in this frame her clock is moving, it ticked less by time dilation. So whereas the finish line clock ticked 100 nanoseconds, Alice's clock only ticked 80 times. Okay. So we also analyzed this problem from the frame of reference of Alice, or aka the rocket frame. And in that frame, right, Alice does not move, but we know that at the start of her race, her clock read 0, and at the end of her race, her clock read 80, so we can put in those numbers. We also know that at the start of her race, her clock was synchronized to the starting line clock, so the starting line clock reads 0. The finishing line clock, however, does not read 0, because in the rocket frame, the racetrack clocks are moving, and so we have a set ahead. Okay, and how much is that rear clock set ahead? Well, we're told that in the rest frame of the racetrack was 60 feet long. And this RCA, the rear clock set ahead, was the rest length times the speed divided by c squared, where v here is the speed of the moving clock, 3/5 c, and L naught is the rest frame separation between the clocks of 60 feet. And when you do the 60 feet times 3/5 foot per nanosecond divided by the speed of light squared, you get that 36 nanoseconds. Okay, what we want to focus on in this example is we're going to discover that although the racetrack clocks are 60 feet apart in their frame, we're going to find that they are less than 60 feet apart in the rocket frame, the frame in which the racetrack is moving. So somehow the length of the racetrack itself depends on its speed. That's the main takeaway for today, and the term we're going to use for that is length contraction. All right. And we're going to show that this has to be the case because otherwise we have a logical contradiction, okay? And how are we going to show this? Well, we're going to focus on the rocket frame for now. And in the rocket frame, between the start of the race and the end of the race, the rocket frame clock has ticked off 80 times, 80 nanoseconds. So what that means is that 80 nanoseconds has elapsed in the rocket frame. And we're just going to ask the simple question, if you have an object moving at 3/5 c, how far can that object travel in 80 nanoseconds? Okay, so here's our question. How far can an object travel in 80 nanoseconds if it moves at speed 3/5 c? Well, we know that the distance that it can cover is given by the speed multiplied by the duration or the elapsed time. So it can go a distance given by 3/5 foot per nanosecond times 80 nanoseconds. Okay, 80 divided by 5 is 16. 16 times 3 is 48. Okay, so any object that's traveling at a speed of 3/5 c for 80 nanoseconds will travel 48 feet. Okay, but here's an object, the finish line clock, that's traveling at 3/5 c. And it's between these two diagrams, it's traveling at that speed for 80 nanoseconds. Right? So there's no way that the finish line clock can travel 60 feet in 80 nanoseconds given its speed. It can only travel 48 feet. Okay. But if it can only travel 48 feet, then this racetrack cannot be 60 feet long, right? It has to be 48 feet long. Why 48 feet? Well, that's how far the finish line clock travels, right? If we kind of map this out, showing in blue the starting point of that finish line clock and the ending point of the finishing line clock, the separation between the two is the distance traveled by the clock. Okay, and what we said was that distance is 48 feet, no more, no less. And yet that quantity corresponds to the length of the racetrack in this rocket frame. So the claim then is that the racetrack itself is not 60 feet long, but rather 48 feet long in the rocket frame, and yet somehow it's 60 feet long in the track frame. So the length of the racetrack depends on the speed of the racetrack. And in particular, an object that's moving is shorter than the same object when it's at rest. So we'll often say things like a moving rod is short. Now I want you to notice an interesting numerical fact. We have two different lengths for the racetrack, 60 feet when it's at rest, 48 feet when it's moving, and specifically when it's moving at 3/5 C. So I want you to remember something, which is for V of 3/5 C, we know that gamma is 5/4. And look at this. If I take 60 feet and I divide it by gamma, that's 60 feet over 5/4. 60 over 5 is 12. 12 times 4 is 48 feet. Is this a coincidence that the rest length of the track divided by gamma is equal to this 48 feet that we calculated before? No, it's not a coincidence at all. That is exactly length contraction. So length contraction says that the length of a moving object is equal to the rest length divided by gamma. Okay, and we've shown that that's the case for this one specific example with the specific numbers that we're using here, but we'll show that in another video that it's true in general, using symbols instead of numbers. The term that we'll use for rest length will be L naught, 0 meaning not moving in the frame of reference under study. And so the equation that we'll use from now on is just L equals L naught over gamma, meaning that the length of an object when it moves is equal to its rest length divided by gamma. And remember, gamma is bigger than 1. So when you divide L naught by gamma, you're dividing L naught by a number bigger than 1. That reduces the quantity, L naught. So that means L is less than L naught, right? So when we say moving rods are short, what we mean by that is that L is less than L naught by that factor of gamma. Okay, so we're going to wrap up at this point for now. In the next video, we will revisit length contraction in a more symbolic way. In other words, not using numbers like 60 and 48, but rather deriving this length contraction equation using L naught, and gamma. Until next time, take care and be well.